I'll begin my presentation. Today I'll talk about the VirtIO devices ported for ARM systems. And when I mean ARM systems, I've tested them on ARM v7, but the device specification is for MMIO devices. So any ARM or any other system actually that uses MMIO should be able to use them as I've implemented them today. A little about me. I'm a first year's master student at the University Polytechnic of Bucharest, and I'm a teaching assistant. I've been to labs for operating systems and assembly languages. In the Beehive, for FreeBSD/Beehive, I've worked in processor caching and the guest power of mechanisms in 2017. And since August 2017, it's a work in progress, I've been working on the VirtIO devices. So, why are we using virtualization? Well, we want to use the system's resources better, and we would want to be able to run other operating systems as applications of our current operating system. We would also like to isolate their running environments for security reasons. Beehive is a type 2 virtualization system, and it was created like this in order to have a smaller code footprint and allow us to reuse some operating system mechanism provided by the FreeBSD operating system, such as memory management. On 886, Beehive uses the BVM console, or was using BVM console in its early stages for debugging purposes. Later, the UART has been virtualized, and we are able to use it for communication with the guest, and some other various devices were created and attached to the virtual PCI bus interconnection mechanism. On ARM, Beehive is located at all of 3 privilege levels, PL0 to PL2. PL0 is the user space, PL1 is the kernel space, and PL2 as equivalent to exception level 2 is the hypervisor level. And we have inserted the hypervisor specific code in the heap mode, also known as privilege level 2. Moreover, ARM systems only have the MMIO interconnection mechanism. We have used BVM console to allow us, we have used the BVM console to debug the system in its early stages, but this does not, the MMIO does not allow for automatic device detection, and we will have to assign statically the interrupt numbers of each device. All of them are placed in a flattened device tree specification file, and one specification file is created for each device, non-device board. For example, the VirtIO device console has the following representation in our FDT. It is compatible with VirtIO and MMIO. It has a starting memory region of 0x5000 in hexadecimal and a size of 200. So I might remove this in the future, since later development proven that it might not be useful anymore. The interrupt parent is the generic interrupt controller, and I have assigned it the 22nd interrupt. Communicate with the guest, as I've said, we are using the BVM console. And how would the typical data transfer between the host and the guest work? Well, let's assume you have an application in the guest that would like to transfer data. It is in the guest user space. It will have to transfer data through the kernel space where the driver resides, and after which an interrupt would be transferred. An exception would be generated that would give control to the hypervisor. The hypervisor in turn will have to give access to the kernel module, the virtualization module in the host space to treat the exception, and the exception will then reach the user space where it will be identified as generated by the console. The other way around will have all 4 steps will have to be retraced to give access to the guest application again. And all of this is used to transfer 1 byte of data. As you can imagine, this is extremely inefficient. We have around 8 context switches. I say around because from user space to kernel space, the application can use write and send more than 1 data from the user to the from the user space to the kernel space of the guest operating system. But after that, 1 byte of the data is true. So this might be acceptable for console devices. But if you want some higher throughput devices, say network, this would be completely unacceptable. A network device usually would have to be able to create a throughput of at least 100 megabits of data per second, and this is way beyond what the BBM console mechanism is able to create. So, virtual devices were created by the OASIS Open Committee. They are generic devices and are specified to be able to work on PCI, MMIO, and port maps, and use vert queues to communicate between user space and kernel space. Vert queues are essentially shared memory space between the guest and the host that both of them can access, and data transfers are done through shared memory. There are 6 types of devices, namely entropy, console, network, and block devices. And these are the 4 that were implemented in bhyve for 886 that had been existing previously. And memory balloon and SCSI host, the ones in blue, are not currently implemented in either PCI or MMIO form. I simply translated the code for the PCI devices to work with MMIO. So when I started developing VirtIO on ARM, I was using the QB 2 development board. This allowed me to implement and test the entropy device, and it was working fine. But since interrupts were not delivered, I was not able to implement the other devices since they required interrupts to work. To allow me to further develop the devices, I used the ARM fast models plus virtual platforms emulator, and in this environment, the interrupts were correctly delivered, and I could develop the other devices, namely console, network, and block, and the block device. So, as you might imagine, we have to talk about how the VirtIO devices work. Well, we have a device driver in the guest and a virtual device in the host. There is an initial negotiation step between them to establish which capabilities are accepted by both of them, and after which the device driver from the guest allocates memory space. Because the guest memory is managed by the host, this memory can be used by both of them at the same time. So the device can simply link it to the VirtIOs and use it as is. For device communication, when you want to transfer some data from the guest to the host, the guest can first write some data in the VirtIOs. Usually there are pairs of VirtIOs to avoid some race conditions. So we write data to the common memory space and send a notification to the VirtIO device. Notifications are usually done through that initial FDT space that is mapped by the host at a specific offset from the beginning of the memory location. The VirtIO device then can read the data and the transfer is complete. When we want to transfer data the other way around, the device can write information to the shared memory space, but this time, since the host cannot directly communicate with the guest, it will have to employ the generic interrupt controller and inject an interrupt request there. The generic interrupt controller will then deliver the interrupt to the device driver that can read the data from the common memory space. As you can see, since we are using the generic interrupt controller that might not work on all platforms, say Qubit 2 for my example, any device that has data written from the device that is initiated by the device and not the driver cannot be performed. So when diverging from the PCA implementation of VirtIO devices, I began by creating a separate copy of the files. I done this because I didn't quite know how much of a difference between the implementation was required. I have changed the memory allocation and the interrupt mechanisms because, as Mihai said previously, the interrupts are not compatible between the JIC and the APIC implementations. Furthermore, PCI bus allows us to identify pins for interrupts that the JIC does not allow us to do. Obviously, memory allocation and port allocation are incompatible with one another, and the separate mechanism will have to be employed. So, in the future, I will have to reintegrate the devices because at the end, the changes were not as major as I was thinking at the beginning. We have generic code in VirtIO.c and VirtIO.h files. These are the most different between the implementations. And we have the PCI/MMIO emulation part of the implementation and the interrupt and the part that handles the interrupt. These are somewhat less changed, but and will have to do some rebasing, but I think there shouldn't be much of a problem. The devices themselves are in these files: SockStream, VirtIO console, VirtIO random, VirtIO net, and VirtIO block. And these files are rather similar. They differ in very few aspects. Specifically, as you can see here, these are the only lines of code, the literal lines of code that differ between the implementation. On 886, we have some other functions with some different names, but their functionality is identical to the ones on the right. PCI set config data is identical to MMIO set config rec. VI interrupt init had simply two more arguments, but essentially does the same thing. And set IO bar is renamed to set MMIO main for MMIO devices. I have encountered some issues with the interrupts, since they didn't work on QB board, and actually they didn't work at all when I started developing, because there was a line of code missing in a switch case where a return 0 was missing, and it simply fell through and a wrong value was returned. That was not as bad, but I had a bad file system type on my board. Say we have this code that is actually in the console device, and we have a bind that to a file descriptor that is an open file, and the socket address to a Unix socket. I would have expected that if our file system would not allow us to create Unix sockets, this call would fail, but it didn't. And I had some problems with it, because it simply created a regular file and not a socket, and I was not able to use it as a socket later on. So I had to dig through some file system code before I figured, well, this didn't fail as it was supposed to do. As a result, we have a working entropy device that is when the driver requests a random value, the host can provide it. The console is working, and I tested it with call Unix -L from the guest and SOCCAT and SOCCAT from the host. The network device works, and I can ping interfaces from the host from inside the guest, and the block devices also work, and I was able to mount a device that was also mounted on the host, provided via a VirtIO block device. All the code is available on GitHub, on github.com/FreeBSD-UPB/FreeBSD 3 projects Beehive ARM. And in the end, I would like to extend my gratitude to the FreeBSD Foundation for their financial support during this endeavor. If you will allow me, I would like to show you a little demo, if you can see it. Okay. Let me change the color. You can do that. Okay. Sorry for that. So I'm connecting via SSH to my computer at our research center, and I have a wrapper script that will run the host. Sorry, that will start the. Well, this is awkward. Okay. This starts the emulator, the ARM emulator, with ARM host in it. It is very bare metal. I mean, every file that is in here I added myself line by line. And I also have a, and also here I have a wrapper that will start the guest. Yeah, it will also create a network. It will add an IP to the network interface, the physical network interface on the emulator, and create a bridge that can be connected, that will be connected via VirtIO net to the guest. Yeah. This will take a little bit, but it should start. And I'm just now figuring out that my horrible yellow, yeah, it's not quite visible on the white background. So I'm going to try to go back to the black background for you to be able to see something, hopefully. This was a somewhat unfortunate color scheme from my part. I'm sorry for that. And I have a little script here. You are able to see it. That will add a network, that will add an IP to the VTNet network interface, and add it's a network mask, obviously, and some MAC address. Running this, we'll be able to see that we have indeed the interface with the IP set, and I can ping it, but it will produce some rather nasty output because the emulator, I think it's the emulator that is crying that the generic interrupt controller behavior is unpredictable, and the end of interrupt register was written, but there is no action preemptive level. But as you can see, we do have the ping output, and it reports that the ping is working. I think, yeah, that will be all. If you have any questions. Yeah. Mike.
So a few questions for the file system issue. For the file system issue and the socket.
Yeah.
Did you find what was going on? Is it because you're using MFS root and there is something weird in that?
No. As far as I remember, I'm not quite sure at this point, but as far as I remember, there was an issue because the QBboard 2 installation guide from the wiki said that the file system should be FAT16, I think. And FAT16 apparently does not support Unix sockets or has some issue with them. After I've changed the file system to ext2, there was no issue.
So, okay. From which wiki are you talking about? Because
wiki.freebsd.org/
and we say to install at FAT32?
FAT16, I think.
FAT16?
Yeah.
Okay. Okay, this is completely wrong. The only part that we format at FAT16 or FAT32 is boot part.
I kind of distinctly remember that there was a line saying gpart -t, I think, exclamation point 12.
Yes, that's for the boot part that all the loader, the FreeBSD loader, UBLDR.
Yeah.
But the rest of the system should be UFS. So yeah, it's normal that you cannot do socket on FAT32 or FAT16 file system.
Yes, but I'm not quite sure what went wrong, because indeed just the base file system was wrong, but it somehow created some issue with it. After I rewrote the file system, it worked fine. So I'm not quite sure.
Okay. Another question is, did all your driver was tested under KVM, for example? Like putting a Linux host and creating a FreeBSD VM under KVM?
No, are you asking if I tried running a FreeBSD guest on a Linux host? No, I haven't. I've only ran FreeBSD host and FreeBSD guest. Both in this setup, the environment works.
Okay. The reason I ask is because if it works correctly for FreeBSD VM on a Linux host, at least someone can test maybe more easily, and we should have this driver committed upstream really soon. I mean, we don't need to wait for the beehive part, beehive ham part to be committed to commit this part.
Yes, but I will next try to run a Linux guest over the FreeBSD host. So if that environment works, I think that it should be fine. Or at least I hope. I will try running FreeBSD on top of Linux, but I was hoping someone else did that before because Beehive already existed, so I thought...
Yeah. To my knowledge, nobody did try.
Okay.
So let's make a difference between device drivers and drivers. So Darius implemented the devices in Beehive. The drivers in FreeBSD were already there, both from MIO and PCI. So
even for MMIO?
Sorry?
Even for MMIO?
Yes, they were there.
Okay.
So we only ported the MIO devices. So you already have them in head for a long time.
Okay, I've misunderstood that.
Actually, it was quite surprising for me because the drivers had a beautiful interface. I mean, you could run both MMIO and PCI by simply adding, you know, this driver is compatible with MMIO and everything works fine. Other than that, I'm not quite sure, but I was hoping since the interface was there and the implementation worked, it should be working. But, you know, that's a good idea. I will try that. Thank you. Anyone? Okay. Thank you very much.